Hi, in this session we shall see about the basics of embedded Linux, a brief overview and environment needed for embedded Linux development and how the Linux development flow will follow, and we'll use as a reference as BeagleBone Black and how the system gets boot up with the boot flow and various components present in the embedded Linux based systems like bootloader, Linux kernel and root file system, different components and how we can set it up and how we can get started with that information that we will see over here. Here we have some brief introduction about embedded systems. Maybe everybody knows about it, and I'm just giving that small brief introduction. Embedded system is basically a system designed for a dedicated function or a special purpose. For example, if you are taking a DVD player, its specific purpose to play the DVD, and if it is a digital television, its function to display the digital contents from a coaxial cable. And why we need that embedded system is something like to reduce the power consumption. It should be smaller in size and rugged in using. And we have something like a limited power over the general purpose systems, which is depends upon that the need for embedded systems. Something like if you are developing an water level controller, it can be done with a very small microcontroller, 8-bit microcontroller with a 4 KB or less than 4 KB of flash and 256 bytes or 1 kilobytes of RAM. It can be able to achieve. Basically, that embedded system is developed for a specific function. It has that option of selecting different processor and different processing power depends upon the application needs basically, and which provides something like a little complex in programming, but it is not a very much difficult one. And we have the different procedures will be used for programming and development, comparing with the general purpose system application development. We have something like mostly based on microcontrollers, the CPU integrated with the peripherals required for the target applications. And we should have in mind while designing that embedded products in such a way that it should be very reduced in size and make it compact in nature, and the product cost is a bullet point for selling with increased reliability and performance is needed with respect to that specific application basically. This is the embedded systems. The Linux general purpose operating system, Linux, has been largely used in the embedded system platform, is the largely recognized as a operating system for various applications like media and networking, and we have the televisions, we have the smartphones. All those embedded devices are using that Linux, which the Linux kernel has been ported and optimized for a embedded system, which is called an embedded Linux basically. Embedded Linux is usage of Linux operating system on embedded system products. The Linux kernel and software components will be in the embedded system products, and Linux kernel will be ported for different another architectures, something like ARM, MIPS, PowerPC, Microblaze, Blackfin, Coldfire, and different architectures. And over the period of time, Linux becomes an alternative for a proprietary OSs available in the market. And nowadays, most of the systems, embedded products, are inbuilt with the Linux operating system. If you see the day-to-day life, our lifetime life products, something like a wireless router, it uses that embedded Linux, and some open source framework like OpenWRT is the open wireless router framework, has been integrated to build our wireless router. Some of the products are using that OpenWRT. And we have an digital television or a smart TV, which is mostly built with that Linux kernel is the main part of the software component, and we have something like different other operating systems, different other embedded products like a smartphone, which is based on embedded Linux, all the Android phones which uses that internally an embedded Linux operating systems. And we have that some of the advantages of using Linux over the embedded systems. Basically the Linux kernel source is completely free and open source, and with the backup with the very large community base and openly available end-to-end software that you can able to easily integrate and build your own solution based on the software components available over the open source. Earlier it was very complicated in order to build a new framework or new images for the embedded Linux. That made easier with the help of different tools like Buildroot and Yocto. Those are all the embedded Linux distribution creation tools by easily configuring and customizing that our need of applications, which also provides something like easier upgrades and expanding the features and application needs, and some of the components to be removed, some of the application component can be added. With the easier and simple configuration, we can able to do that. And also the Linux has the advantage of having, it has the complete set of device driver with the Linux kernel, and it also added with a lot of open source networking and telecommunication software stack. If suppose you are building an automotive application, the Linux kernel has the control area network and Ethernet framework that can be used for a automotive application. If suppose you are using for a telecommunication stack, then we have the different stacks like a SS7 stack or SCTP, that stream control transfer protocol, something like those kind of telecommunication and networking stacks, software stacks are already available that provide us to develop the products at the faster in pace. And we can see about some of the devices which uses the embedded Linux. It starts from smartphone, Now it is Android. Earlier, some of the smartphones uses the Qt and OPIE framework, which internally uses the Linux, and we have the digital and smart television, smart set-top box and DVD player, and smart digital watches and automotive infotainment systems. Some of the enterprises and consumer grade networking switches and routers, and shopping kiosk and point of sale terminal and billing machines, and we have an wireless access point and wireless IP camera and smart video doorbell and surveillance camera monitoring. It's not restricted with this kind of application, and much more devices are running with the embedded Linux in order to achieve that need for embedded system products. And this gives that the simple introduction about the embedded Linux. We will see about the different environment and then the different components in the upcoming sessions. Thank you. Hi. Embedded Linux environment. Most of the embedded systems will have separate embedded hardware, and we will be having the development PC, in which we will be having the sources and compilers and generate the binaries for the embedded hardware. The similar way, the embedded Linux development environment involves two parts. One is the development PC, which contains source code and build systems with the cross compiler toolchain, and then a serial console which will act like a Linux console to the embedded Linux hardware. And we have the JTAG debugger, joint test access group, standard JTAG debugging, which can be used for initial board bring up and very low level processor initialization, something like clocks, DRAM interface initialization, that can be done with the JTAG debugger connected with the embedded hardware. In the real embedded Linux system, the hardware gets started with the bootloader, and bootloader then loads that Linux kernel, and Linux kernel will mount the root file system and starts the services depends upon the end application. The embedded hardware and the development PC will be get connected with three mediums: serial port, which is to get communicate with the serial console, and Ethernet if suppose we wanted to download or the images or something like you wanted to use the network file system, or you wanted to transfer some huge data, those kind of applications. Ethernet will, those kind of requirements, Ethernet will be faster one comparatively with the serial port. And the JTAG will be mostly interfaced with the embedded hardware during the board bring up at the very initial stage of hardware bring up. During that time, we does not know whether the processor came out of the reset, or processor clocks are got initialized properly, and whether there is any exception or rising during the clock initialization, or whether the DRAM has been initialized properly, and we can able to write and read back that DRAM data from the DRAM. Those things can be done with the JTAG connection with the embedded hardware. We will see little bit in detail something like the development PC, the cross toolchain and source code build system and the JTAG debugger. There is different kind of JTAG debuggers are available, something like a USB Wiggler, Segger and VDA 2000 and JLink are the major debuggers that we will use in our embedded system as well as the embedded Linux based systems. And we have the serial console, which will act like a console to the embedded Linux board, and we can able to get the serial or kernel bootups and board bootup logs, and it will act like a Linux console that we will see. And we have the toolchain. Toolchain is something like a cross compiler toolchain which runs on the development PC and generates a output code binary for the embedded platform. It contains 4 major components: binutils, which is an binary manipulation utilities, comprises of assembler and linker, and we have the GCC GNU compilers collection included with the C and C++ compiler, and we have an C library which provides an POSIX interface to the application. Something like a Linux systems uses a system call for the application to get communication with the kernel, and then the kernel can communicate with the hardware. glibc and eglibc and micro clibc provides something like a abstraction layer for system call initiation, something like a open, close, read, write, fcntl or ioctl kind of a system calls are abstracted in the glibc. And the next component we have is a GDB, which is a GNU debugger, which allows remote as well as local debugging. And we have the option to get the toolchain from different locations. This is basically for a BeagleBone platform. You can get the cross-compiler toolchain from the Code Sorcery or Linero toolchain. And some of the embedded Linux build system which has the integrated cross-compiler toolchain, or some of them are capable to generate the new one for their needs. Something like a TI Linux SDK has integrated pre-built toolchain binaries, and Yocto has the capability to generate the toolchain cross-compiler toolchain by itself while building. And we have the build root option, and it also has the flexibility to generate the new cross-compiler toolchain, depends upon the architecture, and it also has the flexibility to provide the the pre-built toolchain to use. And we have the options of getting from the Ubuntu packages, which is available in the Ubuntu repository. You can install that using apt install or gcc-om linux gnu eaba hf installs the om linux cross compiler, and g++ om linux gnu eaba hf installs the c++ compiler. And in order to get the source for the complete embedded Linux for the BeagleBone platform, we have that the different options: TI Linux SDK, which is simplified, and it has very easier to get started with this Linux SDK. It's basically a Linux software development kit for AM335X processor. And we have another option, build root, which makes embedded Linux easy. It's provide very easier to build and making our own customization. and it has some limitations with the build has been added with some by some of the applications, and the customization can be done at the easier manner. And Yocto is the most popular one to generate the embedded Linux distribution. And it's not a embedded Linux distribution, it's used to create a embedded Linux distributions basically. For the BeagleBone Black, we have the meta layers that can be downloaded from github.com, BeagleBone, meta BeagleBone. And we have that the other component of development PC that should be something like a JEDEC debugger, joint text access group. It can connect with the board using the TI Composer, Code Composer Studio, or we can connect with the ARM GNU debugger or TI XDS debugger hardware, and it can be used to access and control over the processor registers directly. It's very useful during the system initialization, register settings development. And it can also be used to validate, bring up the low-level hardware like DDR, flash memory, and it's also useful to configure the processor clock registers. And we will see about how we can interface with the JTAG with the board in the upcoming sessions with the U-boards. And developer will use these tools to makes that system configuration is fine and it's able to boot up. And once that the system configurations are ready, we will incorporate into the bootloader and we'll try to make this bootloader up and running in our board. In order to get that the console outputs, we will be using something like a serial console. It's a serial port, works like a console for embedded Linux systems, and it prints the system boot up messages, acts as a console for both bootloader and Linux shell. And also it provides a way to execute the commands in for the bootloader as well as the Linux prompt. And the Linux shell uses the console as using setTTY, which provides the flexibility to generate multiple virtual terminals. And some of the embedded system will have the LCD displays. Even then it has the LCD display. In our real product, we cannot display our booter blocks on the display. It should be some logo. Even if suppose you are see Android mobile phone, it has a display. It does not throws any like Linux kernel booting and system logs and anything onto the LCD display. It just sends out that information to the serial console basically. And this provides some overview of the development PC, embedded Linux component, and we will see about the hardware side embedded Linux component in the upcoming sessions. Thank you. Hi, Linux serial console. A serial port which works like a console for embedded Linux systems, which prints the system boot up log messages and also acts like a console for both bootloader and Linux shell. Provides a way for execute the commands, Linux commands as well as the bootloader commands. The Linux shell will use as a serial port by using the setTTY command, which emulates that serial console the console into the serial port. And the systems which has even with the system having the LCD displays, uses the serial port as a console for Linux SDK. Like an Android phone has the displays, its purpose to display that Android applications and Android icons and the call, incoming call, outgoing calls. The purpose of the LCD display is to shows that the applications and the incoming calls, messaging, those kind of things. In order to monitor that Linux logs and everything, the serial console is used at the back end during the development. Now we will see how we can connect the BeagleBone Black, the serial port, with the system. Here we have an schematics of the BeagleBone Black. Here in that we will be using UART 0. It's a universal asynchronous receiver transmitter. The transmit pin will be get connected with the USB serial device, TTL device. Here we have we should need an USB serial TTL device, which is this one. Yeah, over this one, and we can connect this. Yeah, connect this with the BeagleBone using the 3 wires. One is receive data and another one is transmit data and then ground, basically. Here if you see the BeagleBone Black, there will be a connector, 6-pin connector nearer to that, over here, which is on the right side. If you keep your power plug over here, you can able to see there is a 6-pin connector will be present. That in that we can able to make the interface with the USB TTL device, which has that basically this has 5 pins. First one is 5 volts and ground and receive data and transmit data and 3.3 volts. We does not need voltages from USB to serial TTL, USB to serial TTL device. We are going to use only the transmit data and receive data and then ground. These 3 pins will be get connected with the 6-pin header of BeagleBone Black. Now we can see over here the 6-pin information, something like the 6-pin header. The first pin will be a ground. This was get connected with the ground over here, the ground pin, and the third and then the 4th pin is the receive data, which is get connected with the transmit data over here. And we have the 5th pin, which is a transmit pin, which is connected with the receive data pin of USB to serial TTL. Yeah. Now we got that interface for the serial console. I'm going to power up this board using the micro USB cable, and there is a plug. The micro USB is present below the Ethernet. I can able to connect over here. Yeah. Now I'm going to plug USB to serial TTL device into my system. Yeah. I just plugged the system, and maybe we can able to see over here. Yeah, I'm going to give D message. Now we can able to see the device TTY USB 0 is the device, that is a serial port which is going to communicate with the BeagleBone Black. USB serial will be detected like a TTY USB. Normal serial ports will be detected like a USB TTY S0, S1, S2. The USB 2 serial devices will be get enumerated like a TTY USB 0. Then I am going to install sudo apt install minicom. Minicom is the utility which will be used for serial port emulation. I already installed. It does not needs to be upgraded or anything. Maybe if you does not install, maybe you will get installed over here. And the serial console is an user-friendly serial port communication utility that will be most of the Ubuntu systems will have the minicom to get communicate with the boards of serial console. It will be something like a Teraterm or Hyperterminal present in our Windows systems. Basically, minicom is a text-based serial port modem controller and terminal emulation program. To install that minicom into the Ubuntu, you can use sudo apt install and minicom. That will install the minicom package of Ubuntu. And once we done with that, maybe we have to do the configuration. For that, we will do sudo minicom -s. Then we will go to serial port setup. In that, we got enumerated our USB to serial as TTY USB 0 that we have given over here dev/TTY USB 0. And basically, when we are running that minicom, you may need a administrator privilege. You should run this with the sudo. If suppose you have the user privilege to write and read on the serial port, you does not need administrator. And we have the settings for the serial port with the baud rate of 115200, and it has to be configured for the 8 data bits, and N is the parity bits, and E1 is the stop bit. How we can configure this? We have to press, whenever you press E, you will get the pop-up and you can select the baud rate and the parity and data and stop bits and different informations like a 8 no parity 1 or 7 even parity 1, that which is a commonly used standards that you can select directly with the Q basically. And this gives that the flexibility to configure, and once we configure, we can save this as a default which is going to be used in our complete program. We are saving as this setup as a default, and I'm going to exit. Now I got connected with the serial port. Now I'm going to power up the board basically. I just powered on the board. Yeah. Now we are getting the system boots up. We can able to see the boot up logs, which is coming up with on the minicom terminal. Yes. Yeah, it's boots. Basically, that BeagleBone Black will comes with the pre-installed embedded Linux image into the eMMC flash memory, which is present inside the BeagleBone Black. You just need no need to anything. You can just connect the serial console and make the power power up the board, you can able to see that logs coming out. And we have got that output, and Linux is got booted up here, and I'm going to enter the root as the user, and we got that the commands, we can able to execute the commands, and we can get the output of the commands which is running Linux commands which is running in our BeagleBone Black. Thank you. We will evaluate much more in the upcoming sessions. Yeah. Hi, embedded Linux components. Bootloader, we have an Linux kernel, and we have root file system, and then application. Bootloader is the component which initializes the primary peripherals, something like a SoC clocks and DRAM interfaces, DDR memory interfaces, initialize the serial ports for getting the console for bootloader, and also it has the capability to initialize the Ethernet, and it can able to download the images from the network using the TFTP protocol. Once the bootloader is up, and it loads the Linux kernel from the boot storage medium like SD card or eMMC flash or SATA hard disk into the DDR memory. And once it loads that, bootloader loads the images into the DDR memory, it starts executing that Linux kernel and gives the control to the Linux kernel. Linux kernel will get started executing, and it mounts the root file system according to the boot aux defined in the bootloader, and it mounts that the root file system, which contains the BusyBox, the standard system libraries, and standard system binaries, and services depends upon the end application of that product, and shell scripts and different configurations according to the end product. And also we have on top, once it got the Linux got the shell prompt, it has different application which can be executed based on the runtime scripts, and that will generates that or initiates the applications accordingly. And we have the boot flow of embedded Linux systems, or something like most of the SoCs will have inbuilt initial boot ROM, which does this preliminary job of checking the bootstrap pins, and it tries to load from the bootloader image from that respective medium. For example, BeagleBone Black supports booting from either SD card, micro SD card, or it can boot from the eMMC memory. If you press that S2 button present in the BeagleBone Black, and then if you power on, it tries to boot from the micro SD card. If suppose you does not press the S2 button or simply powering up the system, then it tried to boot from the eMMC flash. Based on the initial boot ROM which boots the bootloader, and then once the bootloader is up and running, and it loads the Linux kernel image from the medium, and it loads into the DDR memory, and it starts executing the Linux kernel and gives the control over to the Linux kernel. Linux kernel mounts the root file systems and it starts the services and application based upon our runtime scripts configurations. Here we have some basic information about the BeagleBone Black. BeagleBone Black is a TI AM335X sit-up processor based hardware, and we have an ARM Cortex A8 and 32-bit ARM v7 architecture, and we have 512 megabytes of DDR3 SDRAM, and it has inbuilt 4 GB eMMC flash for onboard storage and like a flash bootable flash memory. And we have an micro SD card slot booting, which can be used for flashing the bootable images, and we can use that for development purpose. And we have an micro HDMI video and audio integrated output port, and we have USB 2.0 and USB 2.0 OTG ports for the USB host and USB OTG applications. And we have a 10/100 Ethernet port, and apart from this we have 2x46 pin expansion header, which can be used for further connecting other peripherals with the BeagleBone Black. We will see some of the peripherals, something like different switches, LEDs and temperature sensors and RTC, and we can connect with this with the interface with the BeagleBone Black, and we will explore that with the embedded Linux basically. Here we have the brief introduction about the U-bootloader. Basically, U-bootloader is a universal bootloader, which is in short called like a U-boot. U-bootloader is a open source primary bootloader which is used in most of the embedded devices. U-bootloader initializes the very basic peripherals, then boots the Linux kernel from the storage medium. It also does something like image extraction, handling the compressed images. In order to save the image, the storage area, we will use that Linux kernel images, which will be in the compressed format, so that we will save some huge amount of data storage area. That U-boot has the capability to uncompress the Linux kernel image, and it can able to boot it accordingly. It also provides a flexibility to pass the device tree information as an argument to the Linux kernel. The BeagleBone Black, which contains multiple stages of bootloading, which is first stage and second stage bootloader. The first stage bootloader does the very minimal jobs like initializing the clocks and DDR memory, and then the second stage bootloader does the different initialization, something like Ethernet and TFTP or boot logo. All those things will be done with the second stage bootloader. And we can see about the information over here. The boot flow. The boot ROM will start that first stage bootloader, depends upon our bootstrap pin stage. In case of BeagleBone Black, if suppose S2 is pressed, it will boot from micro SD card. If S2 does not pressed, then it will boot from the eMMC flash memory. And the first stage bootloader basically does the memory initialization and clock initialization, and loads the second stage bootloader from the storage medium into the DDR memory, and it starts executing the second stage bootloader. This is the primary boot flow of the bootloader. And we have the Linux kernel. Here we have some brief information about the Linux kernel. Linux kernel is an Unix-like operating system kernel, and which is an open source and monolithic kernel. Monolithic in the sense the kernel space is the one which works in the supervisor mode. Rest of the applications will be running in the user mode basically. And kernel manages all the peripheral hardwares like a CPU, memory and IO, etc. If suppose application wanted to access any of the hardware resources or peripherals, it should be done through the kernel. Because of that, the Linux kernel provides some application interfaces to access the hardware. Something like a system calls is the main interface between application and the Linux kernel. And also the Linux kernel manages multiple user access, depends upon that particular file whether it has the access or not. And it also provides an application interface for parallelly accessing hardware by multiple threads or multiple applications that can be done. And Linux kernel has the capability of having the kernel modules or drivers integrated within the kernel image, or it can be dynamically loaded after the Linux kernel image booted up. And we have the Linux kernel, the block diagram. In this we will be having the memory management unit, and we will be having memory management unit which basically handles all the physical to virtual memory managements, and all the MLOgs and the VMLOgs and kernel memory allocation, driver memory allocations and the DMA memory allocations. All those things will be managed by the memory management unit. And we will be having the device driver interfaces, and Linux kernel has the scheduler and task management, and it also does something like a very low level CPU initialization and file system with the different file system formats, something like ext2, ext4, vfat, and something like jffs2, flash file systems. Those kind of the file systems are supported within the Linux kernel. And we have a networking stack which supports most of the network communication protocols, starting from the TCP, IP, and we have UDP, we have an stream control transfer protocol. All those things are supported by the Linux kernel. And Linux kernel will have the flexibility to pass the device tree informations, so that we can use the same single Linux kernel image with the different device trees. In case of we have BeagleBone, BeagleBone Black and BeagleBone Wireless, all those images can use the same Linux kernel image, but only differences with the device tree information according to the respective boards basically. And we have the root file system. Root file system is the folder structure, contains necessary binaries and libraries needed to boot up with the Linux kernel. And rest of the file systems get mounted on top of this. Basically, root file system is the topmost folder which gets mounted, and for example another hard drives or pen drives that will be get mounted on top of this. And file system used in the root file systems or something start with the ext2 and ext4 in case of a block devices like a SATA, and we have the secured SD card, or we have something like a eMMC flash. All uses something the ext2 or ext4 kind of a file systems. And we have the CramFS, YAFS and JFS2 or flash file system. If suppose we are using the NAND flash, these file systems, NAND or NOR flash, these file systems will come into picture. And generic recommendation for the root file system design, it should be made something like a very small in nature with only very needed files basically. And we have that some information about root file system structure. The bin is the folder which contains very essential binary needed for system boot up, and sbin is the which contains commands like ifconfig, which is not intended for user, which will be used by administrator for configuring the interfaces, something like that. And we have an etc, which is an system specific configuration files will be present inside the etc folder. And we have the root /root, which is an home directory for the root user. And we have an lib contains shared and standard library needed by the applications. And we have the lib modules, which contains loadable kernel modules. And we have a dev is the location where it contains special device file which helps to interface with the different device drivers. /tmp, which is a temporary file storage directory. Whatever be the content will not be available once after rebooting the system. And we have a boot folder to contain the bootloader images, kernel images and RAM disk. And in case of here /mnt, which contains which will be used by the administrator to mount temporarily mount the different points. And /user, which contain user install binaries and libraries. Proc contains the processor, memory, process, device driver. All the informations will be present inside the proc folder. And apart from this, we have the sys folder as well, which contains the classes, informations, device classes, device bus information, and all those informations will be present inside the sys. Basically, sys will be an user-friendly environment. The drivers, the respective drivers can use that sys file system to record or get the information from the Linux basically. Here we have an application. The basic application will be a Linux cell which provides an interface to the Linux systems, which receives an input from the keyboard of using the minicom terminal and executes the program and displays the output accordingly. It allows the binaries to run commands and execute the programs and execute the scripts basically. And always we will call this as a Linux command prompt, which will be denoted by a symbol $. And there is very huge amount of shells are present: Bourne shell or Corn shell, Born again shell or POSIX shell. All those things are present. Normal usages or something like a Bourne shell or Born again shells are used. And application based packages are based on the system needs. For example, if it is a multimedia application, there will be application based on multimedia. If it is a networking application, there will be applications depends upon the networking. That purely application depends upon the product need, what we are going to build up basically. Thank you. We will see about the more information about embedded Linux and get started with the Linux device drivers as well. That we will see. Thank you. Hi. We gone through some different source code build systems: TA, Linux SDK, Yocto, Buildroot. Here we are starting with the TA Linux SDK, which is a software development kit included with the bootloader, Linux kernel and applications, and root file system pre-built binaries. This also contains the bootloader and Linux kernel Linux kernel sources, and with the easier configuration and compilation separately, the bootloader and Linux kernel. It has the pre-built root file system binaries so that it will be a quick start to get started with the development basically. Here we have the brief introduction about the TI Linux SDK. TI Linux SDK is a unified software development platform for TI AM335X processors. This provides quicker paths to application development as well as the board supported packages and development like device drivers and then kernel optimizations that can be done at the very faster rate. This provides easier setup and faster out-of-box access to the demo applications. This contains demo application for each and every peripheral interfaces that we can use that to easily understand and get started with the application development. TI Linux Software Development Kit contains the Linux kernel 4.14.79 and bootloader 2018.01, and we have the Linux cross compiler toolchain based on Linaro, which is GCC 7.2.1. This also has some host tools which also includes something like a SD card flashing tools that provides for easier and user-friendly commands to write or flash the images into the SD card. And also it has some development environment setup scripts and compilation scripts that we will be seeing, and how we can able to use that, the Linux TI Linux SDK, and how can we build our Linux kernel and build that complete embedded Linux image, and how we can flash into the SD card, and how we can boot up the BeagleBone Black with our created SD card image. That we will be seeing in the upcoming sessions. And here we have an Linux SDK architectures, which contains something like a documentation information and training, and we have an example applications for different kind of peripheral interfaces, and we have the scripts. And for the Linux, we have an Linux kernel, and we have the bootloader. It also contains the cross compiler toolchain based on the Linaro, and it also includes that Linux distributions, the pre-built Arago distribution root file system binaries, which provides easier path to get compilation, faster compilation, and get started with the quicker way to get started with the embedded Linux boards. The embedded Linux setup environment which we already have the path of serial console by connecting that UART 0 of BeagleBone Black with the USB 2 serial device, that we can able to see the minicom, and we can able to use the minicom as a serial console for the BeagleBone Black. That we have already gone through that, and we have the option something like ETH0, and both the Ethernet can be connected, and which can be used to download the kernel image using the TFTP, and we can also use that root file system which can be present in our host PC, and using the NFS that can be the BeagleBone Black hardware platform mounts that this root file system folder as a root file system to it, and it can able to use that in the BeagleBone Black, which gives that faster application development as well as the kernel module development that we will be see in the next upcoming sessions, how we can set up that TFTP server and NFS server, and how we can establish the communication with the BeagleBone Black to the root file system. We will get started with the Linux software development kit, and where we can download and we can compile. That we will be seeing in our next sessions. Hi, Linux software development kit for TI EAM335X processor can be downloaded from the link ti.com/tool processor SDK EAM335X. Basically we can download this. I'm going to copy over here. It's loading. Here we have an processor SDK EAM335X that we can able to download it from the internet. Maybe we can get the software, and here we will be having the binaries to get installed, something like a TI processor EAM335X 006 and Linux x86 install.bin. Maybe we can download this, and I'm going to save. This is around 3.8 GB. It will get downloaded. It started downloading the package, and we can able to see over here that in order to install, once it got downloaded, we have to change something like there is some updates. It's something like 06 00. This is the latest one that we are downloading now, and once we got downloaded, we will be change that permissions, and we have to install in our systems. That let it download. We shall wait for 5 minutes, 5-10 minutes, so that the download will gets completed. I'm waiting for it. Hi, yes, we got downloaded. That we'll see. Okay, we got completed with the download, and maybe we can do that over here. I'm going to install this one. Maybe it was present in downloads. I'm going to move to my local folder, project BBB downloads. I'm going to move it over here. Then I'm going to change the permission chmod plus x. I'm adding that the execution permission to this 06, which is the latest one. I'm going to now we can do that something like executing that the TI processor SDK by using /TI processor 06 install.bin over here, and it will open that setup, and we can do the next. I'm going to do highly recommended that the user, or specifically new user, installs that into 16.4. This is the environment to develop. Basically that the TI Linux SDK supports 14.04 or 16.04 or 18.04 is the suggested installations, and I'm going to install in my 16.04 over here, and I'm going to do next submitting, and by default it will install over here. Instead of that, maybe we can change our location wherever we need, and something like I'm going to change it to my location, home Navy, and then projects, the projects BBB over here, and I'm going to give OK, and the installation path will be something like TI processor. The Linux x86 is the one. I'm going to do the control insert, and going to install over here. Next, it's going to install directory will be over here, and I'm going to give next. Its setup is now ready for beginning the installation, and it started installing into the location which we have given over here. Once it completes the installation, we will be getting that bootloader, U-boot, and Linux kernel sources, and the setup scripts, and Arago distribution, root file system binaries, and applications, demo application sources, and the respective build scripts. All those things will be present inside the installation directory that we will see once after the installation is get complete. Maybe it will take some 3 to 5 minutes, depends upon our PC. Actually, the binary size is around 3.8 GB. It has to extract, and it has to put the informations that it will have. It will take some more time. Yeah, we will wait for it to complete. Yeah, I'm going to pause. Yes, it got completed with the installation, and we got the setup has finished installing the TI processor SDK on your computer. Then we can click finish, so that we will be getting that installation of TI SDK for AM335X processor has been installed in our system over here. Maybe we can go to the installation directory by using TI processor. Ours is 06. This is the directory in which we have the different files which are all available. Something like a bin will have that the binaries needed for compilations, and board support will have that information about the board support packages, something like a U-bootloader, and a Linux kernel, and something like a pre-built images, and additional drivers with respect to AM335X. And we have an docs folder which contains the documentation about the Linux SDK, and different example applications, how to run the example applications. And then we have the example application sources, and then the file system, and we have Linux development kit which contains the cross compiler toolchain and everything. And we have the scripts to create the Linux dev.sh, and we have the makefile, and setup.sh is to make our set up our development PC with the TFTP server, NFS server, which provides a simple scripts which automatically setups the TFTP and NFS server needed for the development. Yeah, we got installed with that TI SDK in our PC. We are going to set up that TI SDK environment by using the setup.sh, by running that setup.sh over here. Yeah, here it asks for something like in which directory do you want to install the target file systems. Something like the target NFS is the one is directory does not exist, it will be get created basically, and this basically we can give this path to a path for NFS mounting into the U-boot arguments that we will be seeing. I'm going to give just enter to continue with this. Yeah, and we have then we have something like the some of the command requires administrator privilege to access on our host, and we have to give that submit our return so that it can able to get the sudo access accordingly. And then we have the TI SDK will contain different kind of two different file systems of Arago distributions, which is something like a TI SDK rootofs image, and we have TI SDK Docker rootofs image. That the Docker will be something like a little advanced image that it can be used for some added with the Docker functionality, and we can install that the file system, which is minimal file system of TI SDK rootofs image AM335X. I'm going to select the rootofs 1 over here, and we have to give that password for our sudo access, so that if suppose any of the commands needed the sudo administrator access, it will get used by the setup scripts for the setting up our system. I'm going to enter my password. It started. Basically, it extracting that TI SDK rootofs image into the target NFS folder. It needs some time, maybe 1 or 2 minutes it will take to get extract that complete one. And now we got the things something like we'll export the target file system into the for NFX access. We have to give a return over here by using enter, and now we got something like we got updated with the NFS kernel with our rootofs file systems, and we have something like then we are going to do with the TFTP server in order to load the Linux kernel image from the network. That we can able to do by entering the TFTP boot is the default location for a TFTP server. That we can continue by entering over here, and we can do the return. Something like we already have the since I have installed the older one, I already have this one. I'm going to do overwrite and I have the different files which may need to get override. Maybe if it is your first installation, you does not need to do overwriting for you. Yeah, successfully installed, and it also provides some scripts to set up the minicom as well. We can enter which serial port it has to use for the minicom. Maybe we can use dev/tty USB 0, which is an serial port device node get detected whenever we plug the USB TTL serial device. Yeah, and something like we have auto detected the IP of our host is something like 1.6 is the one which I got detected. If you wanted to change your host address, then you can change your IP over here, and then we can do something like select the kernel location to be present, and whether it can be a TFTP or it can be a SD card. Maybe we are going to develop that Linux kernel device driver as a module. I'm planning to have the Linux kernel image in the SD card itself. I'm going to do with the 2. The option 2, and then we have that the select the root file system location, whether it is a NFS or it is an SD card. Maybe we can first try with that SD card directly, then we can move forward with the NFS setup. Yeah. Yeah, I would like to create, and there is no board got detected, assuming general purpose EVM is used, and I'm going to skip this one. And we can able to see our board using a minicom terminal as we see in the boot up logs over here. Then we have done with the TI SDK setup got completed, and we got the setup of a TFTP NFS server needed for the needed for our development. Basically, this TI SDK with these scripts gives that easier setup of TFTP server and NFS server for our need. This will be a very quick start for the developers and beginners to get started with the embedded Linux. Now we can have the TI SDK can be compiled, and it can be the images can be generated accordingly, that we will be seeing in the next sessions. Thank you. Hi, now we have set up the TI SDK. We downloaded and installed the TI SDK, and we have made the setup the TI SDK with TFTP server and NFS server got set up. Now we can build the software development kit. In order to build the software development kit, we may need to install the dependency Ubuntu packages for building the SDK. Those are the packages, or something like a build essential, autoconf, and then automake, and we have the Bison, and we have the Flux, and we have libssl dev and BC and uboot tools. All these Ubuntu package dependencies to be installed in our development PC, and we can install it over here. And I have already installed here. Yeah, here I am going to install the dependencies. Yeah, now I have already installed the dependencies. Now the latest SDK has some build issue. In order to overcome the build issue, we have to remove the sysroot from CC and CXX. CC is the compiler, C compiler, and CXX is the C++ compiler. Basically, that environment variable to be changed, that we will see inside the live Linux dev kit. There will be a file called environment setup, and we can go to the location over here. Yes, the CC and CXX, these two are the files. Yeah, now I'm going to remove the for CXX as well. Yeah, yes, we did that change, and now we can do that make all to compile all the software components of Linux SDK, and we can do that make u-boot for in order to compile only the bootloader, and we can make Linux in order to configure and compile only the Linux kernel. Since it is downloaded as a fresh and we have installed into this PC, we can make all so that all the software components will get compiled and install will get built accordingly. Yeah, here the build will take some time, around 5 to 10 minutes, depends upon our systems, and it's just started compiling the Linux kernel now, and it will compile the applications then, and it will compile the u-bootloader, and it will create the copies that binaries into the root file systems. Basically, that we will be seeing over here. It will take 5 to 10 minutes. I am making a hold of it. Yeah. Yes, now we got compiled that TA Linux SDK, and we got the applications, and we got that Linux kernel, and we got that u-bootloader. Everything got compiled now with the make all command, and we can now we are in a good shape to flash that u-bootloader and Linux kernel images, and then root file system images into the micro SD card, and we can try booting from the micro SD card now. Then the next session we shall see about flashing into the SD card and booting from the SD card. Yeah, thank you. Hi, let's install that TA Linux SDK, install binaries into the SD card. The Linux SDK provided with the scripts to make the installation writing into the SD card at the easier and quick start. We have the scripts which is create SD card sh, which is present inside the SD wherever we install that the TA Linux SDK. Here we have here we install the project BBB /TA SDK. Here we have installed our TA SDK. Inside here, sorry, there is something. Yeah, Inside here we will be having bin create SD card.sh. This is the file which creates the SD card, which partitions the SD card and writes that kernel, image and everything into the respective partition, and creating that and writing that the complete root file system into the SD card. All those things will be done by this simple scripts that we will be see over here. I have the SD card and then I have the SD card reader, and I'm going to flash it over here. That I'm going to insert this into my Ubuntu PC over here. I got connected and I'm going to see whether there is anything. We got connected with the SDB and SDB2, and we can run our script sudo bin create SD card.sh. I'm going to run. It will ask for a password, and I'm going to enter my password, sudo access password, and I think I have typed wrongly. Now we have connected only one SD card reader with the SD card. Here we are getting the available drives as 1, which is an SDB. We can select that. If suppose we have connected multiple SD card drives, we will be getting different one, and maybe here only one we have, and I'm going to select the device number 1 and giving enter. And we have the options to create the different partitions, whether our SD card should be partition 2 or 3. If suppose we want, we can select 2 if we need only that the partition, one partition is for boot and another partition is for rootfs. We can have it with the 2 partition. If suppose we need we can create a 3 partitions if we need a SDK and other contents on the SD card that we may need to create with the 3 partition. I'm going to, the default one is 2. I'm going to select the partition of 2 over here, and it's creating the partitions and partitioning that rootfs, partitioning the boot area, and partitioning the root file system area that it is doing over here. It will take some 5-10 seconds. Maybe we shall wait. It's going in process. Basically we will be having that 2 partition. That partition 1 is the boot, which is based on the FAT file system, and partition 2 is for root file system, which is based on ext4 partitions. Basically that partition 1 will contains that bootloader and bootloader and first stage bootloader. All those things will be present inside that the boot for the partition 1. The AM335X, that initial boot ROM, will understand only the FAT file system. Because of that, we need to create with the first partition of FAT, and inside the first partition we will have our informations like a bootloader, first stage bootloader, that is MLO file will be present inside the first one. And partition is now done. Continue to install the file system. Would you like to continue? Yes, I'm going to continue with yes. And we can have it something like 2 options to install. We can install the pre-built images from the SDK, or something like we can enter the custom boot and root file system paths. Maybe if suppose we have the images that is present and out of the SDK, that we can give the path. I'm going to give the install pre-built images from SDK over here, and it's going to install now, and enter the tarball, something like the root of us image is, which is a simple one, and root of us docker root of us is added with the Docker facility. I'm going to select the simple one, and now the uboot.img got MLO and uboot.img got copied, and it's partitioning that, copying that files root file system content into the system partition, system root of us partitions. It's writing. The progress will be around 28%, and it will take 5-10 minutes. 5-10 seconds. 10 minutes. You cannot hold for 10 minutes, right, to flash. We shall wait for 10-15 seconds. It will get over, and this completes that copying that first stage bootloader of MLO and second stage bootloader of uboot.img, and then root file system with the complete root folder structure that we will do that. And it may take another 5 seconds. It is taking some time. Maybe we shall have to wait for some more time, maybe 10 more seconds. It's around 73% now, and it's 74. It's writing into the SD card, and we can use this SD card to boot from boot with the BeagleBone Black, that we can able to do that. And once the flashing got completed, that we're going to use this. 84% is done, and it maybe hardly 10-15% that we will wait. 90. It's around 95%. I think it's going to complete. Maybe it's getting time over here. It's 99%. It's okay. We shall hold for it. It has to get complete. Yeah, it reached 100%. Yeah, almost our flashing procedure has been done, and now it's something like the copying of complete root file system into the system partition has been done. Now it is syncing with that, the all the uh, cache which are available in the file systems, Linux file system, or syncing into the drive. We shall wait. Maybe it will take around 10-15 seconds to sync all the data into the SD card. Yes. If suppose you remove that the card reader before syncing, there is always a chance of getting loss of data that we have to come across. That it is better till we have to wait till the sync has been completed, and so that we will be having the reliable data on our SD card basically. Yeah. Yeah, the flashing got completed. Yeah, we remove it and connect it with the our BeagleBone. Yeah, let's see. We will see on the next session. Thank you. Yeah, now I have the SD card which is flashed by create SD card.sh scripts. I'm going to plug this into the BeagleBone Black over here, and there you can able to see there is a switch which is present. S2 is the switch to select either it has to boot from eMMC flash or it has to boot from the SD card. We have to press the S2 before power up. We have to keep on pressing, and then we have to insert that USB cable in order to get that power up, make that system to boot from micro SD card. I have connected that USB to serial TTL over here, and yeah, and I'm going to execute minicom. Yeah, I think it got not detected. Yeah, maybe I'm going to unplug and plug it again. Sorry. Yeah. Now it got opened. I'm going to press the switch S2 over here, and then after that I'm going to power on with the USB cable. Yeah. Now it's booting up. Yeah. System is getting booting up over here. Now we will confirm whether it's booting our image or not, and whether it's boots from micro SD card or not. That we have to check, and we will confirm that. Okay, let it get booted first. Yeah, we will see whether it comes up to the Linux prompt or not. Yeah. Yeah, we got up to over here. I'm going to do that root and enter. Yes, we got the Linux shell prompt over here, and we can see whether this is our build image or not. Yeah, we can able to see that Bootloader, which has been compiled on July 7 today at around 10. Yeah, we got compiled. I compiled today, and I can able to see the dates and time over here. That should be fine. And we have in the Linux, we can able to see the same thing over here. and which is something like we can do with the uname -a is the command, which gives that it has been compiled with the July 7 over here, and it got compiled. Yes, yeah, it's basically booted with that our created images of TI Linux SDK, and we will see that how to set up an NFS in the next session, and we shall move forward with the development sessions further. Yeah, thank you.